All right, good morning, or good evening, or good afternoon, everyone, from wherever in the world you are joining us. Thank you for joining us for this October 2021 BrainX Community live session. We have some very exciting talks later, but more exciting than that is the work that BrainX Community has done to revamp its website. So just to give us some idea about BrainX Community, for those who are joining us for the first time, we started this 3+ years ago with the idea of following machine learning in healthcare for good. We have grown to 3,000 plus member international community. Rather, I would say now it's almost 4,000. And few of our areas of content are available to you through the brainxcommunity.com or brainxai.org websites, the very active LinkedIn group, where we share a lot of scientific information, and then these monthly sessions, which are very helpful and educational to our community in understanding and help in collaborating with each other. Now, this is the new look webpage, and thanks to the contributions of many on BrainX, this is live now, and it has a lot of enhancements that we have brought about compared to the last webpage that we had. You can see that on the web page, the latest updates is ramped up. It's really nice, it's neat and clean, and you can just click on some of these links and get to some of these posts that are there directly from here. And of course, if you click on the view all, you are able to see all the posts related to each one of these sections, whether it's podcast, connect, or learn. Now, the Connect section is the area where we host our prior talks. So if you miss a talk, you can always go there. This is where we host the announcement for an upcoming talk. So if you want to know which is the next upcoming talk, you can find that out. You can read more about who are the presenters and the topics, etc. And of course, this links to our YouTube channel where you can go. Please subscribe us, and you can get the past talks which have been recorded and made available to you. As I said, we have a very active LinkedIn group. This is just a snapshot from recent times. 1,900 plus international members with a very diverse background. Physicians, clinicians, I should say. We have various machine learning engineers, data scientists, entrepreneurs, people from a whole host of backgrounds, students who are trying to learn and trying to understand how AI can impact healthcare, and they can learn more about it. The Learn section has been revamped, so it has a curated list of articles where they are categorized. They are available to you through a filter function now, so you can filter for your own specialty, since they are categorized based on different specialties. So you can filter for your specialty of interest, and you can look at what's most popular, and you can look at what's BrainX exclusive. Again, here it's showcasing the filter function. So you can filter it by different specialties. You can filter it by different dates. And now we have added journals too in the same format. So you can filter for your favorite journal, and you can see what's the latest and greatest in there. We added a new section to highlight some of the books because everybody's looking to learn more. And you can filter our Learn section for books now, and you can find the recommended reads right over here. And many of the BrainX community members have contributed to these books. And of course, one of the most popular sections that we have is the data section. Again, now you can filter it based on the topic. So you can find data related to your favorite specialty and direct links to these open source data sets. And once again, this is one of the largest open source registries for links to open source data sets. Again, one of our very popular features is the podcast. So you want to learn from some of the experts from around the world. BrainX Talks, it's brought to you by Dr. Ashish Khanna and Alok Kothari. So you can listen to all these conversations and learn how these people navigated their careers in this field, what's the latest and greatest they're working on, and what's next for them. Meetings and conferences has also been revamped, so you can look at the latest meetings, upcoming meetings, register for them via the links provided over here. And this is an additional feature that we have made available to you. Again, this has fostered a lot of transcontinental collaboration. This is one of the examples. The recent paper on TEHI with working with Dr. Sandeep Reddy is another example of that. So the platform has been created to foster this collaboration. And earlier in the year, we showed how every specialty or healthcare specialty has had expanded areas of research. If you want to learn about data, that is there in the general section. So if you look at the 2020 year in review or the prior year in reviews, and you want to learn what are the publications related to data specifically, they can be found in the general section. And of course, the individual specialty publications do contain some information about the data related to that. So again, this particular session is focused on data, and we have some great speakers, Dr. Ashish Khanna, who is also the co-founder of BrainX and BrainX Community, Dr. Kamal Maheshwari, who's again the co-founder of BrainX and BrainX Community, both of them with extensive research backgrounds, extensive collaboration backgrounds, and then very proud to feature our BrainX interns, Raghav, Awasthi, and Shreya Mishra, who've been working with us, and in a short period of time have been very successful in developing some unique solutions for AI, but have also helped us learn what are some of the challenges while we deal with data in healthcare. And with that, I'm going to transition it to Dr. Ashish Khanna, who's our first speaker, who's going to talk about how to do some database research. Ashish, over to you.
Yeah, Piyush, thank you so much. I hope I'm audible and everything, right?
Yes.
Okay. So, I wanted to keep this fairly high level and, just make this a open discussion forum, because we have some good expertise in the house today, in the form of you yourself and Kamal, and then also our research interns who are working with us. Um, my biggest lesson that I have learned over the years with database mining and understanding data is the fact that we forget that laying the foundations of the building is really the most important thing as we embark on all these journeys for trying to develop prediction models and so on and so forth. So what I would really like the audience to take away today is the fact that if we don't have a robust process um, for a internal data warehouse and a process for converting that data into a solid data mart where we can extract data easily, but also the fact that most of us who are clinician scientists should also have some understanding and knowledge of how data is extracted. A lot of times I've actually seen, and I'm sure you have discovered this as well, is we read all of these great manuscripts that have several hundreds and thousands of patients, but no one really talks about the code that was used to extract the data. And that is sort of kept in a black box somewhere. If you read the statistical methodology of most manuscripts that come out as the standard retrospective research where associations are generated based on either relative risk or attributable risk or so on, there is no one is going to share with you the SQL query that ran the data set or so on and so forth. And I really feel that that is something that we as clinician scientists and the community really need to take a hold of and almost ask for it when we do peer reviews and when we critically appraise these manuscripts. Some of this work goes on to affect our clinical practice. We well know that lots and lots of large prediction models and relative risks and attributable risks and so on have affected the way we work on our patients clinically. But sometimes I do worry that at the back end, we're not very sure of how the data got in and how the data was pre-processed. And as I have discovered in the last few years or so, and especially this last year, where I've really focused my attention internally at my institution, trying to work on how we look at our data, how we clean our data, and how we extract our data. I've started to figure out that there is areas of significant improvement, and one of the things there is educating clinician scientists that understanding of data extraction as a process is really, really important. And I'm actually going to open it up to you and Kamal and everyone else on the panel to sort of jump in here. Like, what are your experiences on trying to run data queries yourself? You think that is something that is doable, or should we still, sort of segregate that task to our data analysts?
No, actually, I think that's a great question. Would love to hear Kamal's thoughts because he, of course, has done a lot of research work and has been leading outcomes research here at the Cleveland Clinic, and very proud to announce that he is a recent recipient of an award for his work in outcomes research. So, Kamal, do you have any thoughts? My feeling is that it's an important task because, as we know, it's garbage in, garbage out. And while you're right in pointing out that we need to know the details of how the data was acquired and how it was pre-processed, I think we do need to learn or understand better how the data was pre-processed. So most of the studies will address how it was acquired, through the IRB or which database they looked upon. But a lot of time the pre-processing is scanned. And I think there is an opportunity to have guidelines where a supplemental should be a requirement about the pre-processing techniques. How was missing data handled? How was bias handled there? How some of the pre-processing was done to ensure that it's a balanced data set. So yes, most of the studies, good studies, will provide like a high level approach to this, but I think significant details are usually missing even from some of the good studies. And I think there is an opportunity to have a good framework for that.
No, so those are good points, and I think Kamal is still not fully logged in, so I'll wait for him to give his comments. But I guess it also brings us to the point of what we use as our data sources, right? So over the years, we've been very reliant on, traditionally in medicine, we've been reliant on using the EMR. And as we have well know, EMRs were not really set up to do research. At least the initial versions of the most popular electronic health record systems that we use in the US were not really systems that were set up to do clinical research. They were systems to help with coding and billing. So hospital systems could effectively get reimbursed for services and so on. And part of this was, at least in this part of the world, was something called, the High Tech Act and meaningful use of data and so on and so forth. The one problem as I step back is, where we're getting data from. If the electronic health record is the source of our data, we do realize that there are inherent problems in the way data is available within the electronic health record. Um, most of us don't realize is that when someone goes to an EHR to get data, they're not looking at the front end of the EHR as most of us, log into an EHR vendor. We look at the front end where we can see lab values and vital signs. Someone who's going to get data is looking at, the data cache or clarity or some other module that's running in the back to continuously collect data. And that is where things can sometimes get very messy. One wrong query can result in lots and lots of missing cells on the data that's generated, or values that are irrelevant, they don't make sense, doses that don't make sense. And no one really has the time to, look at 500,000 patients and go through every single value to see if everything's correct. So I'm almost hoping that, someday, and I'm sure Piyush, you have an opinion about this, that, instead of using these kinds of methods to collect our data or do electronic data extraction, that there would be easily available deep learning processes that would be able to actually check on your data and actually alert you on what looks like artifactual data before you take it to your statistician.
Yeah, no, I think that's a great point. So a few different thoughts around it. That is some of the work in many different ways that Raghav and Shreya are helping us with, where you use the tools themselves or the techniques of AI, machine learning, or deep learning for that matter, themselves to help curate the data and create a better cultivated data set. So that is something that we have worked on. I'm happy to announce that the work of Raghav and Shreya was recently accepted at the Data AI-centric workshop of NIPS, which is pretty prestigious. So they will be presenting that. We'll let them talk more about it. But I think you're right. So recently I ran a query. Here's an example. I ran a SQL query, and then another data scientist ran a SQL query. Because the other person did not have the contextual information, there was a difference in our query results. What I was querying was different from their query. So I think that understanding of what is the source truth or the ground truth is extremely important in trying to do your query. And you're right, there is a difference sometimes between what's there on the front end and how it's mapped out to the back end in a relational database. And there can be a difference of the values that you generate out of that. So that's an important point too. But that's where you have to validate the data before you go about pre-processing it or further developing models. You have to validate the data. Now to go back and answer your first question about who should do it, I don't think it is necessary that clinician always should do it, or every clinician should learn how to do it and they should do it themselves. I think data scientists are very good at it. They are probably more efficient than us and more knowledgeable than us in many ways. So we do trust them and we do work with them, but the key is working with them. And that's where I think of it as a semi-supervised model, where you are providing the key things, and that is something that worked out very well with Raghav and Shreya when we worked with them, and they can probably talk about it more. That we were able to provide guidance which makes this extraction and pre-processing more efficient. Otherwise, everybody is trying to figure out what's the right thing, and then if you make an error, then you are starting from scratch again or redoing the process. So if you can work together and provide that semi-supervised environment, then I think it's a better and more efficient working environment. I do see Kamal joined us too over here. So if he has any thoughts.
Yeah, and specifically, this is, I think, a great segue for Kamal, who's done a lot of work on physiological data, specifically, blood pressure streaming data from that gets into the EHR, or that's directly derived from devices. And we all know it's always a struggle to optimally capture granular blood pressure data. Kamal, do you really see a good way out? Because we do know that a lot of blood pressure studies, for example, are always going to be retrospective. It's very difficult to do prospective hemodynamic studies, as we well know, for various reasons. And as we rely a lot on what devices are providing us, and EHRs are providing us for blood pressure, for example, how do we improve the quality of these numbers that formulate the basis of all of our research?
Yeah, good morning, everyone. So it's nice to be part of this panel. I was listening to all the discussion, and ultimately, as data is the raw material for this AI revolution, which is gonna happen. I'm not saying it's, because I think the work, even in the biggest of the industry people to biggest of academic organization, the work is just getting started. There's not much movement has happened. Few areas people have worked on where this data is, like radiology and you know, pathology, but there also it's like the work is in infancy. And this is my opinion. With regards to how do you make it happen in healthcare, right? So one is the structural change, which we have talked about earlier, that neither the healthcare or physicians or people who work within the healthcare have a capacity to build the AI which is needed for healthcare. Neither the industry, who has the supercomputing power to AI engineers, they have contextual information or have knowledge to make it happen. So it'll be a very unique field that if you want to make or see progress in AI in healthcare, it has to be with collaboration. And frankly, I don't see good signs of things happening in the right direction. There's a lot of the questions regarding privacy, security, and who's going to fund this kind of research is been there. So that's been a struggle, but things are moving. Not all is bad. The work which I believe, as you mentioned too, regarding the physiological monitoring and how it's going to happen, eventually it's going to happen in the ideal state in the Internet of Things platform. And what eventually it would be is that every information which is generated from any source, be it a monitor, a machine, which is there or being used in healthcare, including electronic health records, is coming to one platform. And that information you are able to process and use at real time to make ultimately point of care decision making, right? So to close the whole loop. And that's what's the ideal state is. How do you make it happen? You know, we are pushing our organizations to try to make it or move towards that direction. If not, make it happen. At least you nudge them slowly to make it happen. Health IoT is embraced by some companies because eventually it'll be a cloud-based system to some extent. A lot of algorithm development which is happening is local, one single data set. You know, frankly, generalizability is so poor. You know, I don't think one algorithm will going to change at that level. So that's where we are, but we do have some rays of hope, and I'm going to show a couple of algorithms which have worked in, but that is a very small component of the so much going in healthcare.
No, absolutely, and great points. And I guess one thing that we sort of forget is the fact that data is not just generated in the operating room or the ICU or places inside hospitals, but they're also generated when patients, you know, wear devices at home. For example, you know, they use their glucometers to check their blood sugars and so on and so forth. So patient generated data is also extremely important. And really one of the challenges I foresee in the next 5 years or so is to, like you said, Kamal, is to capture every bit of this data, because patients are themselves assuming responsibility for a little bit of their healthcare, generating their own data. We don't have a good system of capturing some of that. We sort of rely on self-reported data. We don't really know, for example, when a patient comes to the operating room, you know, they might be checking on their own blood pressure at home every day for the last 1 month, but that blood pressure data is lost in a blood pressure machine that they've kept at home. The only blood pressure number we see is the blood pressure number that is in the EMR when they went to their doctor's office. And when we try and base our blood pressure management on that one baseline that they had when they went to the doctor's office, which might be very fallacious because, you know, they might have been very anxious when they went. So there's an example of where we don't know the patient's baseline physiology because, you know, the patient's blood pressure monitors at home did not speak to our EHRs. There was no communication or a communication highway for data. And I really feel that, you know, if we have to take all of this physiological data to the next level, we cannot forget what patients do outside hospital settings when we try and, you know, do all of these data generation kind of efforts.
Yeah,
absolutely. I think that's a perfect segue for Kamal to talk about his studies, because he's worked on this, and And he has actually done validation of some of these AI algorithms that have been built on this. And that itself is another challenge, right, Kamal?
No, absolutely. I mean, I think from idea generation from bedside that, oh, we think that this can help a patient, to getting a product which is FDA approved and start getting used, it's a 5-year timeline, which I've gone through from a couple of these projects which we talked about. And hopefully this timeline will be shorter going forward. But at the same time, this is like, as I said, out of 1,000 problems, one problem at a time. That's how these things are getting built. And that's why we need a lot of people, resources, organizations getting interested to make it happen, because based on one algorithm, you cannot change the structure of healthcare, neither because what AI in healthcare is promising is that the care will be more precise, care will be more efficient, and care will be safe. So if you let the computer do certain things, these 3 goals cannot be met. That's why physicians who have so much of information, much more than what is there represented in data, we're going to still survive. So with that, let me just share my screen here. And so if you will, I mean, with that in mind, knowing that the work for AI in healthcare is huge, and as I said, it has 3 major goals: that to provide value-based, efficient care. And so if you say AI is basically, okay, bunch of different algorithms coming together to make point of care decisions, then what you need, what we start with, Ashish started by data sets, right? You definitely have to have the information coded in silico now, right? If somebody's saying something, all information sets has to come, and they has to come beyond one organization, beyond one data set which somebody got, because different population behave differently. The contextual information and is very important. As simple as glucose readings or information which you're getting from an outpatient setting in which patients are managing their diabetes on a chronic basis, compared to somebody who's inpatient setting in which they've been on insulin infusion, right? Where you draw the lines, how you are treating based on that information, what treatments are happening, they're totally different. And that's why the context of all the information has to be very, very important. And that comes from collaborative effort. And, a lot of unsupervised learning we have tried to do, getting some information just to build some hypothesis. But I think in medicine per se, I think there's a room for supervised learning right from the get-go with clinical expert, because they do have intuition, experience, and biology is science-based. I mean, even if we think that we cannot predict a lot of things, but there's a logical sequence of events. So you start with experts right from the get-go, and then but like, even if you build an algorithm, let's say people are predicting like a readmission mortality to is this is a cancer tube, this is cancerous lesion or not. You built an algorithm, you gave some F-score numbers or AUC numbers or R squares, whatever metrics you're using. Algorithm does well, you have done well in, let's say, different patient population. Frankly, nobody does that, but let's say you did it. Now you have an algorithm. What do? How do you bring it in a clinical workflow? That is a huge, huge challenge, because what people do with the information provided to them is very interesting, and we'll talk about it. And does it change certain decisions which were supposedly not to be done or to be done? How you build continuous learning into it, right? The algorithms, the way the medicine works, like you do a project in 3 years, then you start another project, then next 3 years, then another project next 3 years. That's how NASH timelines comes into play. but how you build hourly continuous learning, daily continuous learning, monthly continuous learning into your algorithms. And then finally, did it help the patients? And what I mean by that is that you built an algorithm that this tumor was good or bad, or it's cancerous or not, or you build an algorithm that he's going to die or not. Yeah. Okay, so that is the information, but did you actually help a patient like me, my health goals? You use an algorithm to make it happen, to change certain decision, then my outcomes becomes better or my cost reduced. That's what I care. That's what the value which I'm looking into. So I think there's a lot of work which is bench to bedside translation, which is going to happen, should happen, and we have done some work and we'll talk about it. So you start with obviously right clinical questions, of good data set, supervised learning and contextual information with experts, and then you say how it's going to be implemented. So we have focused on that, okay, because the work then becomes so huge that AI in healthcare, oh my God, what's going to happen? What's going to happen? So, but at least we have said 3 core areas. So I give an example of perioperative intelligence, which is during this, when people are going for surgery, but this applies for any setting. That what is the role of AI algorithm? Like, how does clinician work or physicians work? In all cases, they are trying to identify some high-risk patient versus low risk. We are always trying to risk stratify somebody, that you are high risk for cancer, you are high risk for this, you're high risk for that. So risk stratification is a huge deal, which happens: risk for treatment, risk for getting a lab, risk for getting a bad outcome, good outcome, risk for higher cost or not. So these are all risk. And what we are judging all the time is what is the risk of something. And so you have to identify low, medium, intermediate, high risk. Then the normal course of any illness or healthcare is okay, is sorted out. You can code it. You don't need AI for that. That, for example, if you have a certain infection, you give penicillin, right? So we know that for a fact, right? And it does not require AI for that. But what it is, like when you deviate from the normal behavior, that means what is the risk of complications? The complication means deviation from normal behavior. So how you detect that early, right? How you define what is complication. So early detection of complication becomes very important. And the third is the timely and effective treatment. That when you see these deviation in care for any particular chronic disease, acute disease, be it an ER or outpatient setting, and then comes down to that, did you treat it timely? And did you treat it with most effective treatment, right? These are the data which come from medicine. And here there's a room for AI and all this thing. And this work happens with the input for everyone. And if you remove perioperative intelligence from the center, you put any intelligence, healthcare and AI, this is what exactly it is. So with that in mind, I'll give you 2 examples. One is, in general, the blood pressure is measured very frequently. A lot of data is available. And from a decade of research, we have shown that low blood pressure of certain limits in the hospital is bad, right? And then it comes, okay, can you reduce it? Then hypertension reduction, we know that if it happens, it's going to help people or improve outcomes. So the way you divide this problem is like, can you predict when it's going to happen? With the same theme, which we can, so prediction is that when it's going to happen in the future for certain characteristics of the patient. Can you diagnose it as early as possible? Because sometimes we are not monitoring patient continuously. So you diagnose it, and you diagnose why also hypertension is happening, right? So that goes into the diagnosis part. And the third component becomes the treatment. Like, what do you do if you know it's going to happen, if you know that it's already happened? what is the right treatment at that time. So a simple problem divided into 3 different areas. Now let's focus on prediction component only. Now Edward Life Sciences is a critical care company. We worked with them, and ultimately they developed a hypertension prediction algorithm, right? So they can predict hypertension in the operating room and ICU. That algorithm is built. Multiple papers have been published that, okay, it works in 1 or 2 different populations. Okay, so then the question is, okay, let me apply randomly in my patients. And if will it actually reduce hypertension or not, right? Forget about treatment right now. Does it actually work? So in the last, both the trials which I'm showing on this paper was published last year. They started pretty much at the same time. One is in Amsterdam, one is in Cleveland Clinic here. So my friends in Amsterdam, they started early because approvals came early, CE approval and all the stuff. So they randomized 60 patients, 30 in each group, 30 with HPI, 30 without HPI. And ultimately, they found significant reduction in hypertension, right? So, wow, it works. In 60 patients, you have that it does reduce the endpoint, which is hypertension. We randomized 213 patients at Cleveland Clinic during the same time period, like 4 times the size. And we did not see a reduction in hypertension, right? And then you say that, okay, it's the same algorithm, which was validated and all the stuff. Why did not? Because practice patterns are different. The baseline amount of hypertension is different. From where you're reducing, that is different. What people do when prediction is given, that is different. For example, in our case, only 50% of the alerts were followed by appropriate treatment. So that becomes the implementation component of this thing. So even the prediction algorithm, the 3-component problem solving, which we were doing, after 2 trials, like, oh, what do we do? So the subsequent step is we had just, in fact, only yesterday, I got an IRB approval from Cleveland Clinic, and we're going to start a SMART BP trial. This will be the largest 1,490 patient trial across the United States, in which we're going to use the HPI algorithm and the treatment algorithm, both, because we want to make sure the intervention happens and see if that improves outcome, right? So it's a logical progression of the literature or testing of a particular algorithm, right? The second question, which I'm going to go to, is a common question which happens in clinical care, be it critical care, emergency room.
Kamal, can I ask a quick question to that? I followed the first HYPE trial data, and I was fascinated that they did see such a strong response. Do you think that could also be because the data set from which it was derived was in some way a little bit closer to the testing set? Is that possibly one reason where that could have confounded where there's significant response? And then the second question is, I worked a lot with arterial waveforms and photoplasmography, and those signals, those sensors are also influenced a lot by basic vendor algorithms, right? So depending on which manufacturer is building those algorithms, they may do certain things like apply auto gain, which manipulates the morphology so that it's easier to read, but underlyingly can be affected by artifacts. So could that? Go ahead.
Okay, so there's 2 questions here. One is, why did they see such a significant effect? And as I said, that when we talk about effect in statistical sense, you have a baseline rate, which is the control rate, and you have after post-intervention or the randomized or treatment group rate, right? So yes, the control rate, control means that where no intervention was used or HPI was not used, the baseline amount of hypertension was very high over there, right? Very high on their side. And then the moment the intervention happened, they have significant reduction. Makes sense? So you have a large effect size. Compared to, in our state, our baseline hypertension was low to start with, right? And it was difficult to show any significant improvement, right? In fact, our baseline hypertension rate was same to their intervention group hypertension rate, same patient population, right? Because they both protocols were the same. The second effect, especially in the prediction algorithm, is like what you do after that. So 80 to 90% of time they intervened, they did something. So it was recorded. And compared to in our group, only 50% were intervened. So that also led to, so there was two major factors by the difference in results, which have happened. That's why we are testing the larger trial. And so we're going to look into outcomes now also. But we are convinced that it does happen. The second question, what you're saying is that these algorithms are based on proprietary software and proprietary algorithms and so on and so forth, right? And that will remain true. If another company builds another algorithm, right, of hypertension that requires the same quality of the waveform which these guys are using from the same sensors. So Edward Life Sciences have 3 or 4 different type of sensors. And for this particular HPI, they're using Acumen sensor, like this very specific name. So even within the company, they cannot use different sensor to build this algorithm. And so generalizability beyond using their product is low.
And sorry, I missed it. Was it the radial artery that was being used for monitoring, or was that?
Yeah.
Okay. There are possible artifacts that could come from radial.
So that part goes at the level of algorithm development. When you do test it, so those are sorted out at that level. And this is implementation, So yeah, I mean, those things we know that's happened. There's what can or cannot be done, which waveform you use to predict. You should have certain quality of data to predict. So you're absolutely right about that.
Rishi, I think those are some great questions and thoughts, but let's reserve those and more for the end, because we have a couple of more speakers to follow. So we'll be happy to take those. Thank you.
And this is a second slide. I'm going to finish in 1 minute. So the second common question is like when to give fluid, and if you go to any hospital and doctor, you say that everybody's like, oh, let's give this thing, and that is the biggest question. And then the whole question was, can you build an algorithm? So, okay, there's an algorithm which was built, which is assisted fluid management. Okay, during the development phase, this work is going also on over a decade, with collaborators. The then next logical question is, okay, you test it out, right? So you get a provisional approval from FDA to test it out on a large trial. So with the large trial, what happens? And what happens in this, just to simplify the whole thing, that you have so much of different signals which is coming to you. The question was, you want to make a yes/no decision based on that, give fluid or not, right? And that's what the algorithm was doing. So this was the result of that. This is published a couple of months back. So this was 330 patient, multi-center, like all major academic centers in the United States were involved in this. We use algorithm and say that the first is how you define the fluid is given to be right? That this is the time to give it. So we use the definition of stroke volume increase, that whenever you give fluid, stroke volume should be increased. So if you look at the graph on the right side, on the blue is that when software said, please give fluid, and people actually gave fluid, right? Then 60%, actually it was 66% of the time, there was an improvement in stroke volume, right? Compared to on the orange slide, when clinician, me, thought that, hey, let's give fluid, I think I should give. And only 40% of the time, the stroke volume increase. So what it does mean is that AFM this algorithm did his job in a larger, in overall United States population type, that it can be used to improve stroke volume, right? Then safety data was also reported in this trial. But then the next logical question is that, okay, we achieved the goal. Now, if we achieve the goal, does the patient outcomes improve or not? So that's what we're going to test next. So that's what's going on. Thanks, and we'll listen to Raghav next.
Yeah, thank you, Kamal. That was awesome, and I hope that is helpful. As you can see, it is not easy dealing with data, whether it is for your initial building of algorithms or all the way, developing validation. So I'm gonna have Raghav and Shreya follow up with their presentation to talk about some of the interesting work that they have been doing, and get a data scientist or engineer's opinion on the challenges that they face. So thank you, Raghav and Shreya.
Okay. Thank you, Dr. Piyush, and thank you all of you. So is my screen visible and am I audible?
Yes.
Okay. Yeah, so before moving ahead, I would first like to thank all the BrainX team to have faith on me. I have worked a lot with the BrainX team member. I have learned a lot. So yeah, in this talk, uh, I and Shreya will basically explain some of our experience in data science, the challenges we have faced while data analysis, data manipulation. Uh, so basically, about myself, I'm a PhD scholar at IIT Delhi. I have completed masters in mathematics from IIT Kanpur. And my core area of research is quantifying the impact of socioeconomic factors on healthcare decisions. And since I'm a mathematics person, I have a background in mathematics, so I'm hungry to explore the mathematics in healthcare decision models. So moving ahead, the overall goal for the data-driven decision making is to provide personalized care through right intervention to the right patient at the right time. And the quality of data plays a key role for the decision models. A lots of variety of data is floating all around the world, like EHR data, genomics data, behavioral data, and public health data. And the most important thing is that every data has their unique challenges. If we think about the EHR data and we take clinical notes data in EHR, we can see the data is very unstructured. So finding the critical information from that EHR data is very much difficult. Similarly, the genomics data is very heavy. It needs a lot of storage capacity and the computational power to analyze the genomic data. Similarly, the public health data and behavioral data have their own challenges. So in a couple of slides, I would like to explain some of the challenges related to the clinical notes data, public health data, and my friend Shreya will explain the challenges with the genomics data. So the challenges for the data can have a different level. For example, challenges can happen at the collection of data, like Dr. Ashish and Dr. Kamal have explained some of the things. Data can have data challenges can have at a time of manipulation, like how to deal with missing values, how to deal with spatial and temporal things, and challenges can happen at the time of data analysis. Okay, so let's start with the data, with the EHR data. So here I have snippet discharge summaries. So discharge summary is basically uh, an exhaustive source of medical information, where all the information is summarized in the sections. So here we can see I have highlighted the sections in yellow color. So the sections are like discharge medications, discharge diagnosis, and energies. So if we want to go for a diagnosis or a medication, so we have to follow the two steps. First, we have to go to the some particular sections related to that things, and then we have to move the another step for either diagnosis or the uh, medication. So the main challenge is here, these discharge summary, the data is very unstructured and there is no pattern for finding or annotating these particular sections. So for very first, for uh, annotating this section, we have to do the document level annotations. And if we want to annotate or recognize either drug or diagnosis, we have to go in these sections, and then we will able to recognize them. But in the development of NLP models, lots of open source models are available to recognize the drugs and medications, but is still recognition of procedure or many other medical entities are still not open source yet. So the one of the major challenge is the data annotation. Like one of the paper which is recently published, where they have annotated uh, the 1073 rare diseases. So basically what they have done, so they have randomly sampled 500 discharge summaries, and three of the scientists have annotated all these discharge summary. So which is basically very hand engineered task, and it takes a lot of effort a person to manually annotate these things. So yeah, this is one of the challenge when just annotating a diagnosis, which is a very central theme of all the medical information. But if we go beyond the diagnosis, it becomes more difficult. So just to solve the annotation problem, one of the paper has been recently published. Uh, but this paper is based on the image data, but we can directly adopt these annotation problem to the text data or any other data set. So what the authors have done basically in these papers, they have proposed a human augmenting AI-based labeling system in which initially untrained deep learning models learns human demonstrations and train themselves and begin to augment human annotation ability. And this approach was basically just to reduce the human workload while the process preserves the annotation quality. So this one is the effort where AI models plus human effort combined can reduce the workload of annotation. And this is a very interesting paper for the image dataset where they have annotated the different cell types of the from the biological images. So yes, one of the solution can be a semi-supervised way where AI models can help humans to annotate the datasets. So moving ahead, uh, so I would like to discuss about, because if we think many of the disease happens because of the many societal factors. So just dealing with the EHR data is not a permanent solution for any fixing any disease. So if we deal with the public health related any problems, I'm just here giving the two examples. We need to have a multiple data sources. Like if we take the example of mental health. So mental health is basically dependent on the socioeconomic factors, comorbidity, and also social behavior, like how much some a particular patient interact to their friends, their family, what are uh, their income, and these factor also, and this factor basically causally impact some particular public health related problem. So the problem here is that when collecting all these different information, so these information are not available at a same platform. If you want to capture the governance data or some financial related data, we have to go to the suppose World Bank website. But if we want to take healthcare related data, we have to go to the WHO website. So taking a different data from different platform and then integrating in a spatial way and temporal way is a very much challenging task for the public health problem. So yeah, so for the public health, and my area of work is based on this, how we can integrate different socioeconomic variables, different disease related variables to develop a decision AI based decision model for particular healthcare related problem. So yeah, so I have worked a couple of these problems. The recently we have built a optimal vaccine allocation strategy in the India. So yeah, again, the vaccine allocation also depend upon lots of factor. What is the COVID dynamics? What is the what is the ratio of people who are older in that particular area. So again, here we have integrated different COVID variables, different hospital facility level variables, different age-related variable, population density variable, and we have learned reinforcement learning models to optimally distribute the vaccine in the different states of India. Similarly, we have worked on the mental health uh, problem in United States. Here we have to integrate a different kind of socioeconomic variable and different what is the behavior of a person with his family, how much children in their family, because the children can make the environment happy. So the one of the major finding from this study is that one of the finding was that the income of the particular person, their interaction with their friends and family. Similarly, I have worked on the AMR problem. So the where we have integrated the governance variables, financial variables, burden of disease variables uh, to the AMR data. So we have a data from the 73 countries, and also from 2004 to 2017 of those around approximately 6 lakh isolates. So with this AMR data, we have integrated the governance, financial and health, disease related, and also environmental related variables. And then we find out what are the causal determinants of antimicrobial resistance. And we have found that the government policy like rule of law has a very much causal impact on the antimicrobial resistance. And further, we have um, build a prediction model for predicting the antibiotic susceptibility. And again, we have found that the governance is one of the major predictor for the predicting the antimicrobial resistance. So yeah, again, so the for the particular for the public health related problems, the integrating different data sources, extracting from different platform is a very much challenging task. From here, I would like to invite Shreya to continue the talk. So Shreya, I'm going to stop presenting my screen. You can continue from here.
Yeah, thanks, Raghav. I hope my screen is visible.
Yes.
Okay, so a little bit about me. I'm a PhD research scholar at IIIT Delhi and a research intern at BrainX. Mostly interested in finding applications of data science and graph analytics in omics and healthcare datasets. So taking the talk further, I'll be talking more about the challenges with data sets that exist in genomics data. As we all know that a single human genome takes up to 100 GB of storage space. And as more and more data is being sequenced, the need for storage will definitely grow from gigabytes to petabytes and exabytes. And because there exist a few errors here and there in sequencing, base calling, and genome alignment, a 30-fold of more data as a precautionary measure is generated for each 3 billion bases, which leads to a humongous amount of data. So by 2025, it is expected that 2 to 40 exabytes of storage space will be needed just for human genomes. So as such massive amount of data, genomic data is available, what storage solutions do we have for these data sets? We have genome archives as NCBI, European Genome Archive, the Human Genome Project, which is longing on for so long and provided us a lot of data. But the problem lies with these archives that the data are stored on their archives, and researchers have to download those data sets. And the computational overheads lies with the researchers themselves. Another option that we have are cloud storage services, and they are mostly preferred by tech giants because of their elastic scale nature and distribution capabilities that they possess. One such services is is launched by Google Genomics in 2014 to store genomic data. They built it with an interface that would let researchers move the DNA data into their own server farms, and they can do the experiments using same database technology that Google uses to index and track billion of internet users. A similar interface is provided by Microsoft Genomics to store the dataset and provide certain facilities to the researchers. And then there are Amazon Web Services, which is used by genome sequencing giant Illumina. Moving on, talking about another challenge that exists with genomic data is privacy and confidentiality related challenges. As genomic data is the most private information about the past, present, and future of an individual, it is very important to keep the people's genomic data safe and confidential. Talking about confidentiality, data collection is always kept anonymous for the people who donate their genomic data, and it will definitely become possible in future to extrapolate anyone's personality from just their genetic data. Supporting this claim, our latest research was published in October 2018 in Science magazine, where they said that more than 60% of Americans with European ancestry can be identified through their DNA using open access genetic genealogy databases, regardless of whether they have ever sent in a spit kit or not. So, which makes people question whether they really want to give away their genetic information just as that. A solution to data privacy concerns with tech giants are that encryption techniques are available and blockchain is being used by every data storage companies, and then there are data platforms that are enabled with best encryption techniques. So last challenge lying with genomic data I'll be talking about is computational challenges. The for genomic data analysis of such large data sets comes up with their additional burdens. They call for doubling data storage needs and high-end computing resources. For example, a de novo assembly of a single 3 GB genome can take up to 3,600 hours of CPU time and using up 870 GB of RAM, which is really large. And then there are ever expanding databases such as NCBI, SwissProt, pan cancer analysis, 1,000 genome project and 10,000 genome projects. They have completely outspaced the ability of researchers to store, process, and analyze these data sets. But with the success of AI and ML in data-driven decision making, new techniques and scalable software systems are now available that can automatically help gain insights from these datasets. And another option available are having high performance computing clusters to make the ends meet. So here I'll add on like one of the papers that I was working on in my PhD, where we had around 2 to 3 TB of data, and we were supposed to use that data here and there in our algorithm that we were trying to build. And it was very difficult to use in that 2 to 3 TB of data altogether because of the limited resources that we had. So there came deep learning handy and helped us solve that problem. So with this, I would like to conclude that AI not just helps with decision of the outcome, but also help in improving data quality. But still, domain experts' insight is still needed to validate the data. But despite all these challenges, AI is growing great in the healthcare field and will definitely keep on providing solutions to the challenges that we face in healthcare field. Thank you.
Thank you, Shreya. And thanks for wonderful insights from both Raghav and Shreya, which go beyond the EHR data and tell us about the structural EHR changes that we face. I know we are beyond time, so if you have any questions, please contact the speakers directly. Our resources are once again available through these multiple content platforms, our website, the LinkedIn, our live sessions, our YouTube channel, the podcast, and my email and our LinkedIn links are available through our website too. So I'm going to end this session. Thank you everyone for joining us, and thank you to the speakers for giving us their expert opinions and guidance on this. Thank you.